So 8.1, Introduction to Search Algorithms. Well, let's go ahead and examine two algorithms that locate an item in an array. So they're both going to be search algorithms, but we'll see that they actually work pretty differently from each other. The first is linear search. The second is binary search. Linear search is also called sequential search. And it works like this. Using a loop to step through each element in the array, linear search compares each element with the search value and stops when the value is found or the end of the array is reached. Linear search returns a value of -1 if the search value isn't present. Otherwise, it returns the position in the array where the search value is found. So if we have an array with Mary, Anna, and Sam, positions 0, 1, and 2, and we were looking for Sam, linear search would start at position 0 and see if Mary is the search term we're looking for, but we're looking for Sam, so we'll move on to Anna and see if that's the search term we're looking for. Answer still no, so we'll move on to the next item, and we'll realize, okay, here we found what we were looking for. So we'll return the position of that element, which is position 2. If we were looking for some name that wasn't in the array, so we would examine the first, second, and third elements, but once we get to the end of the array, what would we return? -1, yeah, exactly, So if we were searching for, Roger, we would return -1. So it's pretty easy to understand. Here's another example. Let's suppose that an array called numList contains 17, 23, 5, 11, 2, 29, and 3. If we were searching for the 11, then we would have to examine, the first element, the next one, the following one, and the one after it, at which point we would have located the 11. So we'd search. Oh, sorry.
3 was 11. There's 11.
Yeah, good call. Yeah. So depending on how you implement it, yeah, really, if there were two 11s, it would just give you the location of the first one. Yeah, that's a really good call. Yeah. Everyone understand that, or? Searching for the 7, which, by the way, is not in the array, then linear search would examine the 17, the 23, the 5, the 11, the 2, the 29, the 3, and once we reach the end of the array and haven't found it, what do we return? -1, yeah. For the 11, we'll return what? Close, really close. Yeah, good call. And that's the idea, of returning. We want to return where in the list it is. Awesome. Nice. So it's the fourth element. So return 3. Here's linear search, just written out in pseudocode. One way to implement it would be to set a variable called found to false, and position to -1 and index to 0. and will index is less than the number of elements, and found is still false, then go ahead and search, and see if the array element at position index is the search value. If it is, set found to true and position to index. Because we found it, so it's like, let's keep track of what index it was that matched. And then here's where the if statement ends. And this is an interesting implementation. It looks like they're adding 1 to index after they find it. So this looks like maybe they're going for something where they'll tell us not the index, but they'll say, like, if it was the first element, they'd actually say 1. Kind of a weird implementation. Yeah, kind of unusual, but here's a linear search function written out from our book. There's actually, honestly, a much easier one that I'd like to share with you. A project called Linear Search. I'll just add a new item. Linear Search.cpp. Here's just some setup. Our linear search. Oh, wow. Our main function. Sorry, not a linear search function. That's not what this is. This is just a main function. And then let's go ahead and put in our prototype for a linear search function. Just taking a string and a string array, and an int for the size. And then let's actually implement it. So it should return an int, since I should main, so I'll put a return 0 there. Should return an int. I'll call it linear search. And I'll take in a string called target, meaning just the search value, and a string array. Let's just call it array, or actually let's not just call it array. Let's call it R. Oh wow, see, this is what I got. Sorry, I got myself confused. I put the parameters for that in the main, I think, between the prototype. Okay, sorry. So I'll just type it out. Our size. Cool. Oh, okay, and for the prototype, I'll put the return value. And then for the linear search, well, how about we just loop through the array. And if we find it, so if array, or we're calling it R at position I equals target, then we should return what? Should we return? Yeah, good call. Awesome. Nice. And what if we make it to the end of the array and haven't, and the if statement was not true? We should return -1. Yeah, yeah. And that's a good value to just indicate that it's not in the array, because the index will be like 0, 1, 2, 3, but it'll never be -1. So yeah, so returning -1 is a good way to say, look through the array, couldn't find it. So in line 9, if we call the linear search function on this array called items, which is the second argument in the way that it's written here, and we're trying to find C, capital C, and we have the size also as 3, then let's go ahead and let's run this program and let's see what linear search has to say about finding the C in this list of A, B, capital C, capital A, B, C. So let's pause things too. Cool. So the search value we're seeing is at position 2. So that's just a nice quick implementation of linear search. I think it's a little more like intuitive than our book has it. So it's returning the 2 because the C, we've got the A at position 1, B at position 2, C at position, or A at position 0, B at position 1, C at position 2. Yeah. What if we change the search value to D or X, something that's not on the list? What would the return value be? -1, yeah, cool. Let's check it out and make sure that our algorithm does that. So the search value is at position -1, yeah. Cool. Or in other words, yeah, it's not in the list. Okay, so any questions about linear search? How many? It's the size of the array. So yeah, it's these three strings, yeah, A, B, and C. It's the size of the array. Oh, good question. If we used vectors, then yeah. Yeah, if we used vectors, then we could yeah, exactly. We don't have to indicate the size. Yeah. Yeah, because we could use like items.size if it was a vector. That's probably a nicer way to do it. Maybe that could be like extra credit or something to change this to. Yeah, or maybe. Oh, sorry. Oh, to change. I think we did this last year. I don't remember extra credit though. Change all all 4, because we'll see 4 search and sort algorithms, 2 search, 2 sort algorithms, and so last year we changed them all from arrays to vectors as like an extra project, kind of like the activity we did tonight. Yeah. So does everyone have that down, or do you need this for a little longer? Anything, anyone? Okay, cool. The benefits of linear search are that it's easy to understand, and the array can be in any order. So, can just be kind of haphazard, and you can still use linear search. And you'll still find what you're looking for, even if it's the very last element, or even if it's, well, you won't find it if it's not on the list, but at least you'll get to the end and realize it's not. The disadvantages, though, are that it's slow. Imagine an array of n elements. If in the worst case scenario, the item you're looking for is where? The first, middle, or last element? The last element, yeah, which would totally suck. We have like a million elements, and the very last one's the one we were looking for. We had to examine all million of them. Or even worse would be if it's not on the list. Yeah, we have to examine all million and only to realize it wasn't even on there. Yeah, right? Yeah. The best case scenario is it is the first item in the list and you're searching in order, and you're searching first to last in the list or the array. And yeah, that'd be the best case. The average case is just the average of the two. So it would be on average, yeah, you have to examine half the array before you can expect to find the element. Which is still not, yeah, which is still like maybe it could be better. Yeah. Because all of these n over 2, those are, it's fine, but there are faster algorithms out there. Okay. So let's take a look at one of them. And first, let me kind of just draw out what this would look like. So let's say that numList had a 2, 3, 5, 11, 17, a 23, and a 29. So there's numList. So binary search is faster than linear search, but it requires the elements to be in order first. So it's a trade-off. But the way it would work, is that to find an element, well, here's just kind of the elements written out as like a tree where the 11 is like the root node of the tree, like the root point in the tree, and to the everything smaller than the 11. Well, there's the 3, and the things that are smaller than the 3 are the 2 and the 5. So everything to the left should be smaller and to the right should be bigger. So the 11 to its bottom left is the 3, and to the bottom right is the 23. And then for the 3, its bottom left is the 2, and bottom right's the 5. 23, bottom left's the 17, bottom right's the 29. So just kind of like splitting up the array starting here, and then we've got these 2 pieces here. And then start in the middle again, and you've got 2 pieces, on either side. And then same on the right-hand side, start in the middle, and then you've got 2 pieces on either side. Binary search requires the elements to be in order, and divides the array into 3 sections. The middle element, which would be the 11. Everything smaller than the middle element, which would be this side here, the 2, 3, and 5. And everything bigger than the middle element. So that would be this side here, the 17, 23, and 29. If the middle element is the search value, the one we're looking for, then we're done. So that would be awesome. If we were looking for the 11, we would just find it right away. We'd be done. If not, we would go back to step 1 and use only the half of the array that might, well, okay, so let's say we were looking for the 3, start in the middle and we'd find the 11, and then what we would know is, okay, the middle element's not the one we're looking for, and since everything on the right of the middle element is bigger than it, but 3 is less than the middle element, we know, okay, really we can restrict our search to the first, like half of the list, or the first of these 3 sections. So just the 2, 3, and 5. Okay. And then we would repeat the process. So let's say we're looking for the 3. Then now our new list is really just 2, 3, and 5. So we'd start in the middle again. And there's our 3 that we're looking for. The best way to do this is with examples, I think. So let's go ahead and do some more examples. So here is numList, and it's got a 2, 3, 5, 11, 17, 23, and 29. I'll go ahead and I'll fill in the indexes too. Got index 0, 1, 4, 5, and 6. And let's keep track of, I'll put F for first. I'll just try to write it out. Last. Crazy. Let me just make it. Finish slide. So here's our array. And there's the indexes. Okay. Let's search for the 5. And let's make a little table of first, last, middle, and the list at position middle. Cool. Okay. So we're searching for the 5. And here's kind of the process for that. So we'll start with first is always going to be the index of the very first element, which is always going to be 0. And last is always going to be the subscript of the last element. So this array has 7 elements, so last is 6 for the positions. So the 0 and 6 are first and last. Middle is always going to be the first plus the last divided by 2. So 0 plus 6 divided by 2, and it's just integer division. So 0 plus 6, so 6 over 2 is what for middle? 3, yeah, And what's in our array at position 3? The 11, cool. So we haven't found the 5 yet, but we know that we can restrict our search to, well, what we could say is we know that the searched item, the 5, is less than, what we found, the 11. So that means we can restrict our search to just, you know, the first half of the array, pretty much. So to do that, we'll have first still be first, but what'll happen to last? Should it be 6 anymore, or what should it be? 2, yeah, cool, And the trick is, well, the last will be middle minus 1. Or if it was on the other side, the last will be middle. If it was on the other side, the first would be middle plus 1. So those are kind of the two cases. So but let's keep going through this example. So middle is always first plus last over 2, so 0 plus 2 over 2. Did you say 1? Yeah, awesome, cool. And num list at position 1 is the 3, yeah, cool. So we still haven't found it, but we're getting there. The 3 is actually less than our search term of the 5. So we'll update first and last, or one of them. Which one? First, yeah, make first middle plus 1. Yeah, so those are our two options. Either make first middle plus 1 or make last middle minus 1. Yeah, so if we make first middle plus 1, it'll be 2. Last will stay 2. One always stays, one always changes if you haven't found it yet. And middle is always first plus last over 2, so 2 plus 2 over 2 is 2. Yeah. And num list at position 2 is the 5. Yeah, So we found it. It was at position 2. Yeah. And so we would return a 2. Any questions about that example? Let's do more examples. Let's use the same array, but let's search for the 7. And I'll clear out this table. Okay. So first is going to be 0. Yeah. And last? 6. Yeah. And middle? 3. Yeah. So it's first plus last over 2. Nice. And num list at position middle? 11. Yeah. Awesome. So the 11's not the 7, so we have to update first or last. Update last. Okay. So keep first the same. And so last, if we're going to update it, it'll always be middle. What do we do? Middle minus 1? Oh, sorry. Middle minus 1 is 2. Awesome. Yeah, exactly. Cool. And then our new middle will be 0 plus 2 over 2. 1. And num list at position middle 1 is 3. Yeah. Cool. All right. We're looking for the 7, but we have a 3, so we better update first or last. Which one? Update first. Okay, cool. Awesome. So first will be middle plus 1. So 2. Good call. Last will stay 2. Middle will be 2. Num list at position middle is 5. Yep. Cool. Awesome. Yeah. And we haven't found it. But first equals last. And when first equals last and num list at position middle is not the search item, then that's enough to conclude it's not on the list. Yeah. Yeah. We would return, what do you think in this case? -1. Yeah, exactly. And in the last case, I didn't put it down here, but we would have returned 2. let's kick it up a notch. So, so 1, 2, 7, 8. Okay, cool. So let's go ahead and try to find the 536 in this array. And so I'll go ahead and delete those down here. So here's our array, and so what should we set first to? 0, and last 8, yeah. Middle's, first plus last over 2, so 4, awesome, cool. And num list of position middle is the 4, 296, awesome, cool, nice. So we're looking for the 536. So we should update first and last. What should stay the same, last or first? Yeah, last. Let's see. Yeah, I think we want to restrict our search to this half. So yeah, last would stay the same, but first would change to middle plus 1. Yeah, so last will still be 8, but first will be 5. Yeah, and the new middle will be 5 plus 8 divided by 2. Yeah, 13 divided by 2, and it's integer division. 13 divided by 2, integer division. Yeah, 6. Sounds good. Awesome. And what's our num list of position 6? Oh, okay, 536. Well, that wasn't that exciting because we just found it. Okay, cool. All right. Yeah, return 6. Yeah, cool. Nice. Oh, yeah, David.
So for this six method, they have to be in order, so 100, you're at 101 to 600.
Yeah, they'd have to be in order, yeah.
How often does that even practical, or is there like a way to sort things and then put it back where it was, or how's that work?
Yeah, for things that you know you're going to want to search quickly, yeah, it's a good idea to sort them or index them first, and then you can easily find them. Kind of like if we had a bunch of names, how we put them in a phone book so that they can be easily found. It's the same idea, yeah, yeah, But as we'll see, yeah, the sorting actually takes longer than the searching. So, yeah, this would be if we were going to search like again and again, yeah, to just go through the kind of like upfront work of sorting it. And then you could find stuff pretty quickly with binary search. Yeah. So should we try to find anything else in this list? Yeah. Okay, cool. Is that enough examples? Do we have a good, okay, cool. We have a good understanding. Cool. Okay, awesome. Well then, let's go ahead and leave it there. So thanks everyone and have a good week. See you next time.
How long do you have to submit that, number 15?
Oh yeah, is it reasonable to ask? Well, I guess there's no reason, if you want to work on it up to next week, yeah, before we meet again on Tuesday, yeah, yeah. Awesome, but it's not worth any points. Oh, bye, you too. Have a good one. But it's just more just like to check everyone's oh, sorry. Yeah, just just to like keep us so we're working in class and stuff. Yeah. Cool. Oh, no problem. Yeah. Do you want to come in office hours or something? I'll be there. Today's Tuesday. I don't have them on Wednesday, but on Thursday, maybe from 11:15 to 1:15.
Yeah, I have to get like to look more and like I think this lab will now too, the lab 7.
Cool. Awesome. Okay. Nice. Yeah, those are good. Yeah. Oh, and the source code examples too. I just posted those tonight. So there's a new link in Blackboard that's just source code, and then you can check out those. That's a good resource. It's worth checking out for sure. Yeah. Bye. You too, Ahmed. Thanks.